Welcome to Afternoon Live. We're on air a little early because in just a couple of moments, astronomers in Washington and Brussels and cities around the world are about to reveal the first ever close-up image of what's been described as a monster black hole. Over the past 2 years, 8 huge radio telescopes placed around the world have been pointing at the centre of the Milky Way, some 26,000 light years away. Well, they've been studying a black hole which measures 25 billion miles across. That's 3 million times the size of the Earth. Now, scientists at the Event Horizon Telescope program are about to reveal the results, including the first ever photograph of a black hole. Well, this is a truly global event. As I say, it's a broadcast moment that they're putting around the world simultaneously in cities from Tokyo to Washington to Brussels. We're keeping an eye on the event in Brussels right now, and I'm joined by Professor Lucy Green, who is an astrophysicist. This is a very, very exciting moment.
It is a huge moment. I mean, people like myself, I think we never thought we would ever, with our own eyes, see light coming from the proximity of a black hole. It's remarkable. I
mean, we've got these images, and I've got them around the studio, but these are guesses. We've seen what Hollywood thinks a black hole looks like, but we're about to actually find out.
That's right. There's been lots of work on the theoretical side for a long time now, so we have a very good idea of what we expect to see. So theories that tell us how big the silhouette of a black hole should be, so that dark region in the centre where light can't escape, what the shape of the ring of light will be around the black hole, light given off by hot, fast-moving material. But will our expectations match the observations?
And what will we learn from this? Gravity, Einstein, this is a moment where it all makes sense or not?
Well, hopefully what we'll see will corroborate and support Einstein's general theory of relativity. And it is interesting to reflect that in science, theories progress, things change. Sometimes ideas are completely swept away, and other times there are incremental improvements and adaptations to theories. So we had Newton's theory of gravity many years ago. That was good enough for looking around us on the Earth, but when we went into the solar system and were looking at how the gravitational field of the sun operates, we needed to make changes, and Einstein came in. So will Einstein need changes, or will he be correct?
Right, well, I'm just going to show what's happening, because this is the news conference in Brussels.
Press conferences,
Let's
so I will break with
join for this historic moment.
And hand the floor directly to European Research Commissioner Carlos Moedas, and then we will turn to the 5 leading scientists here on stage with us involved in the discovery. Commissioner?
Thank you very much. Let me put the timer. Thank you so much, and it's a great honor to be here today. We're really about to announce a huge breakthrough for humanity. We are about to take a picture of something that one man alone, dreamt, imagined 100 years ago in 1915. Albert Einstein. Imagine that. This idea that a very big weight transforms geometry, that when the mass is too heavy, you make a hole, a mysterious hole, where nothing can get out of it, where all is absorbed. Michael Kramer here from the ERC said, the history of science will be divided into the time before the image and the time after the image. And you know, for my generation, it's all about the imagination of something that was in between science and fiction. At the age of 9, I went with my father to watch the movie Black Hole. And I remember coming home and for the first time in my life, 9 years old, thinking about what's the meaning of life? What am I doing here? Is there any parallel universe? That's what really got me excited. And probably the question that we have to ask to us, to everyone here that really loves science, is to think about, what about in 100 years? Einstein was there 100 years ago, but in 100 years, what have we and what will be the discoveries? The things that we'll discover from this knowledge. You know, I see Robert de Graaf there that wrote a great book about the usefulness of useless knowledge. And Einstein could not imagine what he discovered. He cannot imagine that one day, because he created and discovered the antimatter, that would create the PET scan that will save lives all over the world. So I'm really proud. I'm proud of science. I'm proud of science because science today is giving a lesson to politicians. It's showing that today to take a picture of something that one man dreamt 100 years ago, you need people from 40 different countries. You need people from all over the world, that at the same time that you're sitting here, there's 6 press conferences in Washington, in Tokyo, in Taipei, in Shanghai, and in Santiago de Chile. And I'm proud of Europe. I'm proud of Europe because we have invested so much in this project. We have put all together more than 44 million euros because we can be proud that Europe has a winning formula. And that winning formula is simple. We believe deeply in the freedom of science. We believe that scientists are the ones to make the choices, that the choices of science are not done by politicians. We believe somehow in the intuition of science. Stephen Hawking once said something that I would like to finish these words today with you, with this excitement of us. He said, "It is said that facts are sometimes stranger than fiction, and nowhere this is more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact." So, ladies and gentlemen, I think that I've not been this excited since when I came in 2014. If there's a big moment for all of us, is today. And so this big moment is shared with so many in the public, so many today here, and I want to invite all the team. And for that, Professor Heino Falke is here, so he will come immediately to my place and tell you, and we will join all of us here in the room, we will join him unveiling the image. So Professor, please come and I'll go.
Still have to, thank you. Now I have to fill the time actually until we're allowed to actually, start the unveiling sequence. I thought I use the time to introduce our team here that's here today on stage. We have Monika Moshi-Broczka from the Radboud University, working on theory and imaging of black holes. Luciano Rizzola from the Goethe University in Frankfurt. We have Eduardo Ros from the Max Planck Institute for Radio Astronomy. And we have Anton Census, the director of the Max Planck Institute for Radio Astronomy in Bonn, and also chair of the board of the Event Horizon Telescope. And we have, a lot of team members here in the front row. Michael Kramer was already mentioned, our co-PI. You have Remo Tilano, the project manager of the Event Horizon Telescope. I'm glad you're here with us today. Colin Lonsdale, who is the co-chair of the Event Horizon Telescope project. Now we have to start with the session. We are looking into space, towards a galaxy, a giant galaxy, 500 billion light years away from us. Sorry, 500 billion kilometers away from us. Very big galaxy which was suspected to host a supermassive black hole in the very center. 101 years ago, someone discovered a streak of light, which is plasma shooting out of the center of the Milky Way, marking the supermassive black hole. I never believed that this black hole was as big as people said, until we saw that. This is the nucleus of the galaxy M87, and this is the first ever image of a black hole. Das ist das erste Bild eines schwarzen Lochs. Dit is het eerste foto van een zwart gat. C'est la première image d'un trou noir.
Well, that was a moment of history. Let's talk to Professor Lucy Green, astrophysicist at UCL in the Mullard Space Science Laboratory. Wow.
It was incredible, wasn't it? Oh, no, after all the anticipation, actually what we saw was very close to what I'd seen on being produced by the people running the simulation. So you could see that dark silhouette in the centre. That's the really important part of this image. And then the glowing material around that dark heart.
And just if we just show what we've just there it is. That is the image.
Yeah.
That is the first time mankind has seen a black hole.
Yeah.
So tell us about the light around it. It looks like it feels a bit like an eclipse.
It does, doesn't it? Yeah, it does. So in the environment around a black hole, material is captured and is orbiting that central mass. And whilst it's orbiting, we're not exactly sure how, but the material is heated up, and it's also travelling very fast, so it's giving off light across the spectrum. And this project in particular measured the radio light coming from that vicinity of the black hole. But in the centre, you have such intense gravitational fields that matter can't escape and light can't escape. So there's this silhouette of the dark, very strong gravitational heart of the black hole silhouetted against that bright glowing material.
Now we need to put some scale to this. What we're looking at, that black hole, that's 3 million times the size of this Earth.
It's remarkable.
We're talking about a big thing.
Yes, it's enormous. So, and the black hole at the heart has a mass, billions of times the mass of our sun. So it is worth just reflecting on that, the enormity of that object. But at the same time, in the sky, it's very small. So you need a very, very large telescope to be able to image it.
I'll talk about that with you in just a moment and how they've done this. But let's just return to that news conference in Brussels, because I think we can hear from one of those involved.
You know the story behind that image. We're looking at a region that we've never looked at before. A region we cannot really imagine being there. It feels like really looking at the gates of hell, at the end of space and time. The event horizon, the point of no return. That is awe-inspiring to me at least, but it's also important for physics. I think my colleague Luciano Rezzolla will now continue and explain to us why this is so important.
Questa è la prima immagine di un buco nero. So black holes are part of our daily knowledge. In fact, even a child knows what a black hole is. And the best definition I've received actually comes from a child who simply said, well, it's just a hole you cannot fill. So they're very simple, but they're actually extremely problematic in physics, and because of the properties they have. The first property is that at their center, in a single point, we think the laws of physics break down. We call this point a singularity. Another property is that this singularity is covered by a surface, a mathematical surface, which is called the event horizon. Gravity is so strong on this surface that nothing, not even light, can leave it. And this surface separates the interior from the exterior, and nothing from the interior can leave and be transmitted to the exterior. And for a scientist, this is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms? You come to terms with this idea. Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And that is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed, and so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object, something that we can test and we can measure and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work. And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.
So, an explanation there of what's been achieved. Let's start with Professor Lucy Green, astrophysicist, and I mean, you were listening closely there, and you share the excitement. I mean, scientists are well, this is a magic moment. I mean, there was a wonderful quote, wasn't it? That this is like this is a huge breakthrough for mankind. It's equivalent to seeing the gates of hell.
Oh, it's great, isn't it? But that is the kind of emotion that black holes conjure up in all of us. You know, they've been such enigmatic objects in our minds for so long now, and by their very nature, absorbing or holding onto the light, meaning that it's really hard to study them, but now we can see their proximity. But we all have this sort of passion for black holes because they're so curious.
And well, we're used to Hollywood images. This is better.
Oh, it is better. I mean, on the one hand, yes, it's a smudgy thing, yeah. But what it tells us is so important. And I think it was really interesting during the press conference to hear them talking about the importance of observations. And I'm an observational astrophysicist, so I like to test theories with real data. You know, theories are one thing, they progress our knowledge of the universe, but we have to validate them with what we can see. And so this, for the first time, allows us to validate our theories of black holes with real data.
And we should explain how this has been done, because they've basically turned the Earth into a huge telescope. They've got 8 telescopes around the world and got them all to work together to find this.
Absolutely, it is remarkable. I mean, the challenge involved cannot be underplayed. So there are 8 radio dishes around the world that worked in unison to get these data. And the reason you needed so many was you basically needed to get a telescope that was the size of the Earth. And we can't build that, but we can make one up virtually by using different telescopes. And using an effectively a big telescope means we can see smaller and smaller details in the night sky. So to be able to resolve this as an image needed a big telescope. But there are all kinds of challenges that go with that. So understanding and measuring when the light comes into the different telescopes, precisely knowing the time at which it's being collected, then those data have to be sent to a central processing unit and put together to reconstruct an image. And even one thing I was reading was that you have to take into account the atmosphere above each telescope. So it's radio data that's being collected, and that's affected by, say, the water content in the atmosphere. So across these different sites around the Earth, taking data at slightly different times, different atmospheric effects, you have to account for that. It's a huge challenge.
There are 2 people I'm thinking of right now. One is Einstein, he's had a mention. The other is Stephen Hawking. Who, I mean, what would he have made of this? This was his life's work too.
Absolutely. I mean, it is sad that we're not able to hear his voice on this amazing image, because he had such a good way of of making things understandable and making things tangible to people, and to have spent your life working on black holes, understanding them now we see it for the first time, but it's just too late for him. It's really sad.
It was rather interesting watching scientists who, not perhaps always given to emotion, but this is a life work.
It is, absolutely. You know, to make this project happen, it was years in the making, absolutely years, and they had to push the technique of bringing together information from these different telescopes. They had to push the technique to its limit because they were using a slightly shorter wavelength than is normally used. They had to bring in new algorithms and processing techniques. So it wasn't easy. And then the data started to be collected in, I think it was early 2017, and here we are 2 years later, and finally we've got the results. The data that were collected at the South Pole had to be transported manually back to the processing centre, and then you have to wait for the winter to end so that you can get the physical connection. So there's all kinds of amazing things that came together to work for this.
I mean, this is just the start. You presumably are going to be wanting to look at all the data, and there must be other images, I guess, but...
Absolutely. So one of my colleagues is working on this project. So he's over in the Brussels conference at the moment, and I can't wait to talk to him about it. He's been running simulations to look at predictions that can be matched to these observations. It is just the start. I think you're absolutely right. This is a new way now for us to study black holes. And the question is, where do we go from here? It's the start.
And you'll never forget where you were when you saw that.
Absolutely.
Right here. Thank you very much. Lucy, thank you so much for joining us on what is a historic moment. Professor Lucy Green, thank you very much.